Right guys, today we're going to talk about sound waves, but to do that I first just need to recap the basics of waves in general, okay? So very quickly here, if we just look at our diagram of a wave here, okay, we can remind ourselves that looking at this, we've actually got two complete oscillations, okay? One complete oscillation is going to go up, down and back up to the center here. The second complete oscillation, up, down and back up to the center again. Some key terms. We've got the wavelength, which we represent using this kind of upside down Y. It's a Greek letter lambda. Is from any two identical points on the wave. Okay, so from a peak here to a peak here, it could be from a trough to a trough. The easiest one to draw is usually actually on the axis here, from a point where it's about to go up, down and back up to here. So this is the one I would tend to draw, mainly because it's easier to identify the exact point that the wave crosses the line, whereas at the top and the bottom here, it's a bit tougher because it's difficult to know the exact point that it's at the top. We can get a little bit less precise doing it that way. We've got the frequency, which is the number of complete oscillations passing a point per second. So if you were to stand on a beach, for example, or at the sea, and you've got some waves passing through, you would, if you said there was, I mean this would be exceptionally fast, but if there was 3 waves past you every single second, or 6 waves in 2 seconds, 9 waves in 3 seconds, that frequency would be 3 Hertz, okay? And we've got the speed of the wave equation here. So the speed is simply the frequency times the wavelength. This is the most common sense equation that you will ever find, really, because if we think about it, the frequency is how many waves per second. If you had a frequency of 3 waves per second, that's 3 Hertz, and each wave was 5 meters long, so the wavelength was 5 meters, then it's pretty obvious that if each wave is 5 meters long and 3 of them go past you every second, you are going to be passed by 15 meters of wave in every second, okay? So 15 meters per second. So this is our kind of fundamental wave basics. There's one more little bit of wave basics we're going to talk about. That's the 2 types of wave, and then we'll get on to sound waves. Okay, so the 2 types of wave that we need to know about are transverse waves and longitudinal waves. The key difference is in how the particles are vibrating, or how the wave is vibrating. So in a transverse wave, well, in both of these waves, in fact, the direction that the wave is traveling is, we're going to say, is from left to right here, okay? So in both of these waves, the wave is traveling in that direction. However, the actual particles, their movement is different. So in this wave, okay, you have got things that are oscillating up and down. Things are oscillating this way, and that is perpendicular to the direction that the wave is moving. So if your oscillations are perpendicular to the direction that the wave is traveling, then this is a transverse wave. In this one here, what we're actually going to have is things are oscillating forwards and backwards like this. So they're oscillating parallel to the direction of the wave, or the direction of the energy is being transferred, and therefore we have a longitudinal wave. In a transverse wave, you have peaks and troughs. In a longitudinal wave, you have compressions and you have rarefactions, okay? That's kind of the fundamental basics of waves, very quickly covered. You could spend ages looking at this, but I just wanted to recap it. The reason I needed to go through all that is because what we're actually going to do when we talk about sound waves, I'm going to introduce to you the idea that sound waves are actually longitudinal waves, but we actually draw what looks like a transverse wave just to represent them, usually because it's easier to draw transverse waves and it's easier to take measurements and things off a diagram that's a transverse wave. So when we're talking about sound waves, they are longitudinal waves, but we are going to represent them, we're going to draw them like as if they were transverse waves, okay? So let's move on to sound waves now. Okay, so now this amazing diagram here is basically a diagram of a loudspeaker. Okay, now we're going to actually late in year 11, when we look at the magnets and electromagnets topic, we're going to look in more detail about how these things work. But basically, a very basic idea is that we've got an alternating current and something called an electromagnet. So we're basically going to turn this coil of wire here into a magnet, and because we've got an alternating current, we are going to have that magnet is going to change its polarity, so it's going to go north south, south north, north south, south north. And because we've got a magnet here, this is going to effectively pull and push this magnet away. And then this is the part that's the speaker really, is you've just got basically a cone, like a plastic cone or a card cone or something, and this is going to be moving forwards and backwards. That's all. I'm not going to go into any more detail. We've basically got a system where we've got a cone that is moving forwards and backwards. Okay. Now this cone moving forwards and backwards is going to push the air particles forwards and backwards. So you've got air particles here are going to get pushed forwards and backwards. They're going to push the particles there forwards and backwards. They're going to push the particles there forwards and backwards. And you will get a wave of air traveling you've got a wave traveling through the air like this, okay? Now that is a longitudinal wave because the oscillations are parallel to the direction that the wave is traveling, okay? They're along the same direction, forwards and backwards. And what basically happens with the sound is that the sound is going to travel forwards and backwards. It gets to your ear, it's going to make your eardrum vibrate. The various bones in your ear are tuned so that they you can then interpret that signal. I'm not a biologist, so I'm not an expert on how the ear works, but basically that longitudinal wave travels to your ear, makes things in your ear vibrate, and then you can hear that sound. Okay, so let's talk a little bit about the speed of sound. Now, you've probably heard of the speed of sound before, just like you've probably heard of the speed of light before, but they're two very different things. Now, the speed of light is extremely fast. The speed of light is 300 million meters per second, and it is gonna in a vacuum anyway. Okay, now it does travel at slightly different speeds in different materials. In air it will be slightly slower, but basically still the same as that. It's going to travel again slightly slower in things like light can travel through water or glass, but even in those situations it's still going to be in the order of hundreds of millions of meters per second. Okay, it's extremely fast. On any scale that you're going to use in a day-to-day life, you can pretty much consider it's going to travel from one place to another instantly. Okay, the speed of sound is slightly different. Now this the number that we generally use is going to be something around about 340 or 330 meters per second. Okay, now this is obviously again dependent on what that sound is traveling through. Now, sound traveling through a liquid or a solid travels much faster. So for example, in water, I think it's about 1,500 meters per second, something like that. It might be into several thousands, 3,000 or 4,000 meters per second, traveling through a metal rod. And this is also going to be affected by the how your altitude. So for example, this is probably at sea level where the air has a certain pressure, a certain density. If you go to higher altitudes, this is going to change as well. So these factors all change, but for now, we're just going to consider this here. Now, if you wanted to actually try and measure the speed of sound, there's a pretty simple experiment that you could do. And all you need is you need to get one person to do it with you. You can pretty much go to, say, the other side of a field or something where you've got a set distance and you can measure that distance. So let's say, for example, if I stood here and I had someone who was standing 100 meters away, and you've measured this distance of 100 meters, what you basically need to do is you need the person who is 100 meters away to do something that you can see and hear as well. So for example, it could be that they stand up and they clap their hands. Okay, it could be that if you had like a starting pistol from like an athletics race, which you can hear but also see the smoke come out of it. Anything really that you can see and hear that they happen together. Okay, and basically if this person stood here and they clap their hands, okay, you would basically, you're going to see them do that. Okay, the time that it takes for the light at this speed to travel 100 meters is so small that you cannot notice it. You could calculate it. Okay, you could calculate it. Obviously, time is distance over speed. Okay, and 100 meters divided by 300 million meters per second is a very small time. However, the sound is going to take some time to get there. And if you time it, so if you start a stop clock when you see the person clap, you stop it when you hear that clap, you are going to find the time that it takes for sound to travel 100 meters. And simply, your speed is just going to be the distance over time. So if that time was, it should be, looking at this, about 1/3 of a second. So you would have 100 meters divided by, say, about 0.3 seconds, okay? And that's going to give you in the region of 300 or so meters per second, okay? So you can actually calculate the speed of sound quite simply using a nice simple experiment like this, okay? Now, what can we actually change about sound then, okay? So there are two main things that we can change about a sound. We can either make that sound louder or quieter, so we can change the volume of a sound, okay, to make it loud or quiet, or we could change the pitch of a sound to make it high pitch or low pitch, okay? Now, you need to be aware of what it is about the sound wave that affects these two things, okay? Now, the volume is affected by the amplitude. Okay, so the amplitude being the distance from the top of the peak to the center of the wave, or from the bottom of a trough to the center of a wave, okay? And again, I know that I'm talking about transverse waves here when I should be talking about longitudinal waves, so you can consider it to, the amplitude would be almost how compressed the compressed part of a longitudinal wave is and how stretched out the rare refracted part of a wave is, okay? But it's more difficult to think about it like that. So we talk about it as if it's a transverse wave, even though it's actually a longitudinal wave, okay? The pitch is the frequency, okay? So if you have a high frequency, so lots and lots and lots of waves per second, you're going to hear a high pitch sound, okay? And the sort of question that we can get, I've seen a past paper question, and it looks something like this. So it would show you two sound waves, and again, I know sound waves are longitudinal, but we depict them sometimes as transverse. So it shows two sound waves, and it might say something along the lines of this. So it could say, could have this little wave here, and it could have this wave here. Now, the question I'm thinking of when I've seen this, it was actually a 4-marker, which I thought was very, very generous. And the question said, compare these two sound waves and give reasons for your answer. So you had to come up with 2 conclusions and give an explanation for why you came up with each conclusion. So if we said this was A and this was B, what I'm going to be saying is I'm going to basically make a conclusion about the volume and say how I know that, and a conclusion about the pitch and how I know that. So for A, I'm going to say A has a much smaller volume, much lower volume. So A is lower volume, or quieter. It's a quieter sound, and we know that because it has a smaller amplitude. Okay, so it was a lower volume, and we know that because it has a smaller amplitude. And that was, all you had to do was understand this, and you can get 4 marks in this question. 1 mark, 2 marks, okay? So A was lower volume than B because it had a smaller amplitude than B. The other thing we're going to do is we're going to talk about pitch. So we can then say, and you could say again about A compared to B, but I'm going to write it as B this time. I'm going to say B has a higher pitch and we know that because it has a higher frequency, or because there are more waves in the same amount of time. I think the question also said this was represented by 1/10 of a second or something. But we know it has a higher pitch because there are more waves in the same amount of time, so it has a higher frequency. So more waves in the same time, or in other words, it has a higher frequency. Okay, and this is the sort of question that you tend to get asked about sound, where they're asking you to describe what's going on with two different or a number of different ways, and you really have to understand this, and it's quite simple really. Okay, and that's the idea with volume and pitch of a sound. But what about what can humans actually hear? Okay, so the human ear is tuned so that we focus on this really. Okay, the human ear is tuned to hear certain frequencies, and the range of frequency that a human can hear is between, let's change colour to make this, because the blue's going a bit low. So for the humans can hear between 20 hertz to 20,000 hertz. So from 20 hertz to 20 kilohertz. Now, obviously at the extreme ends of that, we are less sensitive. So I think it's about 3,000 hertz is the frequency that we are best at hearing, basically. But we can hear this range. Now, the top end of this range actually becomes a little bit more limited as you get older. So the older you are, the lower this this top end drops. So for me, for example, my top end here is probably now about 16, 17,000, something along those lines. It drops down, and the older you get, the less able you are to hear high pitched sounds. But in general, these are the two. This is the range of human hearing that we are generally asked to consider. Okay. Okay. Now the next thing that we're going to look at is just another example of how they can ask you a question using sound waves. And we're going to look at something called echo sounding. Okay. Now an example of this, the most common example of this, is as follows. This is also very important for the next lesson, or one of the next few lessons we're going to look at will be on ultrasound, so like ultrasound scans, and they use this process, but I'm only going to talk about it in terms of sound today. Now imagine you've got a boat, okay, and this is doing some kind of survey of the ocean, and you've got the ocean floor underneath, and this boat wants to know how deep is the sea, how deep is the ocean. Well, what they do is they will send a sound wave or a pulse of sound wave down to the ocean floor, and then that will echo, that will reflect. A reflected sound is called an echo. So that will reflect and it will travel back up to the boat, and what the boat will do is they will measure the amount of time it took for this pulse of sound to go this journey all the way to the bottom and back up to the top again. Now this exact same process is also used for things not just for the sea floor, but for finding what is actually in the water. So you might get it in like military uses. They might use it to try and find submarines and things. I think fish, like high-tech fishing now, they'll use it to find where like there's schools of fish in the sea. But we're just going to use this principle for the bottom of the ocean. Now let's say, for example, that if we said the speed of sound, sometimes they use c for the speed of sound or for the speed of light. I'm just going to keep it to v for now. So the speed of sound in water, we're going to say is 1,500 meters per second. Okay, and I'm going to say that the time delay, so that's the time it took for that pulse from leaving the boat to get to the bottom and back up to the top again. So the time delay, let's say for example, was 4 seconds. Okay, so there should be some nice easy maths here. So what we're going to do is we're going to work out the depth of the ocean. So the distance that has travelled is going to be the speed times by the time, which is obviously 1,500 times by 4, which is 6,000 meters. but this is not our final answer, okay? We need to remember that this is the total journey length of our sound here. So we're going to have to half that to find the depth of water. So we can see here that the depth is going to be equal to 3,000 meters, okay? So this is the final thing that, this is the final stage in this calculation. And like I said, when we are in our next lesson, we're going to look at ultrasound. And we're going to look at this in a lot more detail because ultrasound scans and lots of different uses of ultrasounds, they use this principle, but it can be asked in a sound, as a standard sound question as well. Okay, so there's one more thing we're going to look at in this session, and that is the Doppler effect. So I'm going to clear this and we're going to move on to, and I'm going to have a quick talk about the Doppler effect. Okay, so the Doppler effect. Now, this is something that there are a number of different applications of. In particular, we'll look at it at a later date more in terms of light waves as well, but just focusing on sound waves for today. The Doppler effect is actually something you have all witnessed in your lives. Every single one of you will have heard a car go past, or a bike, or something, and it makes the sound where it goes, okay, as it goes past you. Everyone would have heard something along those lines. And the reason for that sound is because of the Doppler effect. Now, if you imagine a situation where you've got a car and it's got its engine running, or it's making some sound, or you've got its beeping its horn, or whatever it is, okay, that sound is going to be emitted the same in all directions, okay? The same frequency in that direction, the same frequency in that direction. And if you had a person standing over here or a person standing over here, this person is going to hear exactly the same sound, the same pitch, the same frequency as this person is, assuming that car there is stationary. However, if this car is moving in a certain direction, what happens is that when that car sends off a sound wave, and it sends off another sound wave and another sound wave, when it sends off its first part of the wave, its first oscillation, it then moves a bit, and when it sends off its second one, it's caught up with that one a little bit, and it's moved away from that one a little bit. So even though the car is sending off sound waves equally in all directions, someone who is over on this side, they're going to experience the sound waves coming to them at a higher frequency, whereas someone on this side, they're going to experience the sound waves getting to them at a lower frequency. So even though the sound itself has been created equally in all directions, there is an apparent change in the observed frequency and the observed wavelength, okay? And that is what the Doppler effect is, okay? So the Doppler effect is the apparent change in the observed frequency and wavelength due to relative motion, okay, so the fact that this car is moving relative to this person, okay, due to relative motion between the source and the observer. Okay? Now, you don't necessarily need to learn this word for word, but you just need to have a pretty good idea about what this is. And basically, we can then say that over on this side, this person, when the car is moving away, or when the two objects are moving away from each other, it could be that the car was stationary and the person was moving away, or the car was stationary and the person was moving towards, so long as it's relative motion. So here, we're going to say that if the source of the sound is moving away, this person will experience a lower pitch, missed a C there, a lower pitch sound, okay, because they've got a lower frequency and a longer wavelength, okay? Whereas this person is going to experience a higher pitch sound okay, because they've got a higher frequency and a shorter wavelength, okay? And this is it. This is basically the Doppler effect, okay? Like I said, there are more examples of it. The most important example of this really that we'll look at in the future times when we look at the space topic really is redshift, okay, which is when you've got effectively the Doppler effect with light waves from long distance stars, and we can use it to work out what the stars are doing, what different galaxies are doing, and all kinds of things, okay? But this one here for sound waves is relevant. You've all experienced it in your day-to-day lives. It's, you know, when a car drives past you, it's the reason why if an aeroplane, you know, when a jet flies over quite low, you don't hear it very long, and suddenly you get a very high pitched sound and then a very long, low pitched sound as it moves away from you. So yeah, that's the Doppler effect, and that is basically the key things we need to know about sound waves. Okay, thank you.